Welcome back to the Math of Machine Learning Summer School. It's my pleasure to introduce Emma Brunskill, Assistant Professor at Stanford Computer Science. She'll be teaching us in the next 5 hours about reinforcement learning. Thanks.
Thanks. I'm really excited to be here. Before we get started, I just thought we did a little bit of a survey before the term started, but I wanted to just check a little bit about people's background. So can you raise your hand if you've ever covered Markov decision processes in AI or ML? Okay. Did you guys cover value iteration? A couple people. Did you cover policy iteration? Okay, a few. Right, so there's more and more hands going down. What we're going to start doing is, and then maybe on the opposite side, who here does research in reinforcement learning? Does anybody? So a couple people do actual research in reinforcement learning, and who here has done a proof with reinforcement learning before? Okay, so a few people have. So it's clearly a really wide background. We'll do our best. What we're going to start with sort of like the very, assuming no background in reinforcement learning at all, and then we'll build up to sort of some of the things that I think are most exciting in this field. Before we get started, I just think it's great to think about the amazing legacy of decision-making under uncertainty. So if we go back to Aristotle, he had this beautiful way of thinking about what a doctor does, which is a doctor doesn't think about, whether or not they're going to proceed. They think about the desired outcome. So they want to get a patient to be cured, and then they think about the sequence of steps that would be possible to achieve that. So they say if someone was cured, what would have to happen in order for them to be cured? Okay, what would that previous state be? How would I achieve that state? And they do this backward chaining all the way back to the beginning of what the current state is of the patient. So he essentially described this form of sort of backwards induction or dynamic programming. And the way that he described this was realized about 2,000 years later by a system by Newell and Simon, who are some amazing AI researchers at Carnegie Mellon in the 1970s. So people have been thinking about and reasoning about how to make sequences of decisions for a very long time. What you've been hearing about so far is really sort of the supervised learning paradigm as well as bandits from Kevin. And you can think of reinforcement learning as really being at the intersection of those and going beyond that. So in particular, reinforcement learning, in the most simple definition, is simply learning to make good sequences of decisions under uncertainty. And I think it's great because it's got, it's an amazing intellectual field and enormous potential applications. This very simple definition actually covers pretty much everything that we're going to talk about because it encompasses all the things we're going to have to do. So learning means that we're not going to know how our decisions affect the state of the world in advance. So we're going to have to be gathering data to achieve that or using existing data to do that. We're going to care very much about sequences of decisions instead of a single decision or no decisions at all. And the uncertainty aspect is going to be critical, though recently there's been a lot of work also on thinking about just sequences of decisions even without uncertainty. I would argue that this is really sort of one of the fundamental challenges in artificial intelligence. Aristotle's thought about it. People have been thinking about it really intensively, at least since the 1940s, which is the earliest. Well, that and sort of Thompson are the earliest known discussions of multi-arm bandits, which we can think of as a simple case of reinforcement learning. Though of course, itself is a huge intellectual field. So it's something that we're going to need to solve if we want to make progress in machine learning and AI. And of course, I think one of the reasons why people are particularly excited about this over the last decade, and I'll remark this is a huge change from when I started in the field. When I started in the field, if you had a reinforcement learning paper, there was maybe 5 papers in a conference. You'd go there, you'd see Rich Sutton, you'd see your favorite 30 people. Now, if I go to ICML, International Conference of Machine Learning, this year reinforcement learning was the only one that I think had parallel tracks because it is such a huge field now. And I took a picture of Andrea Zanetti, who's going to be your TA, because in the theoretical reinforcement learning section, there was at least about 150 people. So this has been a complete sea change over the last 10 to 20 years, and really a lot of that is due to some of the remarkable work that my colleagues at DeepMind have done. So this Atari game, which I remember David Silver talking about in a NeurIPS workshop about 5 years ago, and using pixels and being able to do direct control. In this case, do we move up, down, left, right, or things like that? Direct control of the game from pixels and showing reinforcement learning could achieve human-level performance was really a huge milestone in reinforcement learning, and I think it's been responsible for an enormous amount of attention to the field. That said, I think that there's still an enormous amount of mathematical challenges for us to tackle, particularly if reinforcement learning is going to achieve its promises. So Robotics is the other main application area. My colleagues at UC Berkeley in particular have been doing some really pivotal work. Imo Todorov here. There's been a number of different people who have been thinking about how do we do sequences of decisions under uncertainty for manipulation, for many other types of challenges. Now, in my own work, I'm very interested in how reinforcement learning impacts society and can be used in a societally beneficial way. This is a game actually that was developed by Zoran Popovic here at University of Washington and a number of his students. It's called Refraction. It's been paid by, I think, around somewhere between 100 and 500,000 students. And we started thinking about how we could use reinforcement learning here to try to help people persist and learn more effectively. And I'll talk more about how that might be possible in this paradigm. And then there's also a lot of growing interest now in the use of reinforcement learning for healthcare. It's something my lab works on, a number of different people are thinking about. This is an older example from Joël Pineau's lab, thinking about this for epilepsy and how do you do control to try to achieve desired outcomes. So there's a lot of different types of application areas. We'll go into some of those a little bit more. I think the key things to think about for reinforcement learning and how it differs is that it involves optimization, delayed consequences, exploration, and generalization. And really, so far, you've heard about all three of these except for maybe delayed consequences. So you've heard about optimization, you've heard about the exploration challenge from Kevin. The exploration challenge has some additional complications when we move into the sequential decision-making case. And of course, you were hearing about the generalization challenge just last hour. So why is this different? Well, if we think about artificial intelligence planning, now this picture is sort of in some ways not the best choice because reinforcement learning was used in Go. And in fact, reinforcement learning can be used in cases where we do know the domain for computational tractability. But in general, in artificial intelligence planning, it involves optimization, generalization, and delayed consequences, but where you know what the effect are of your decisions. So in the case of Go, we know what would happen if you take any particular move. There's a rule book, you can look it up. We can give that information to the agent. And so they don't actually have to explore to figure out the consequences of their actions. There might be computational reasons to do that, and in fact there were for Go. But in general, AI planning is different from RL in the sense that you have a model of how the world works. I'll be more formal about that shortly. In supervised machine learning, which you've heard a lot about over the last few days, we always have the optimization challenge, we have generalization, we generally don't have exploration, we don't have to go gather our data ourselves, we're given data in general, we don't generally have delayed consequences, and we assume that we're provided with correct labels. In unsupervised machine learning, we have optimization and generalization. Again, no exploration or delayed consequences and no labels from the world. And imitation learning, who here has heard about imitation learning? So a number of people have, not everybody. Reinforcement learning is both making enormous strides and turning out to be incredibly hard. And imitation learning has been hugely helpful in making practical advances for reinforcement learning, and I think will continue to be so. It's kind of an interesting hybrid. In imitation learning, as it's strictly assumed, we assume that maybe someone's given us a demonstration of how we want the world to work. So for example, I'll show how to pick up a cup. And when I do that, then I want my robot to be able to imitate me. So it's this interesting hybrid because then the agent doesn't have to do exploration. They can rely on demonstrations. But they don't get direct labels of what to do. They just sort of see an example that you might want to generalize from. And it generally requires input of good decision policies. Again, I'll be more formal about all those terms shortly. I do want to highlight imitation learning because it's really the place where we first saw massive progress in reinforcement learning by moving from a strict reinforcement learning setting to imitation learning. And in particular, Andrew Ng managed to fly a helicopter upside down, which was considered an extremely hard challenge, a toy helicopter, by using imitation learning learned from pilots. So this was around 2003, I think, and was one of the first sort of more real-world demonstrations of reinforcement learning, in this case, achieved using imitation learning. Now, I'll skip this for now. There's some challenges with imitation learning that we can talk about, in particular things like covariate shift. So we can talk about those later. So how do we proceed in this case? Well, what we're going to do and talk about a lot is how do we gather data, similar to some of the challenges with bandits you heard about, and how do we leverage that data to guide the future decisions we achieve in order to get high reward. In particular, this is going to be our rough plan. We'll see how things progress, and we'll adjust accordingly. We'll start today, and we'll talk about sort of the basics of Markov decision processes and value iteration. Then you'll have these sort of recitation breakouts, a chance to think about some of this. We'll start talking about reinforcement learning, where we don't know how the word works later today, and then we'll move into some more advanced topics. I just want to highlight this. You've been seeing a lot of really beautiful math over the last few days, and I think that reinforcement learning is a really interesting field because it's both in some ways very mathematically deep and very shallow. What do I mean by that? I mean, if you look at sort of something like International Conference on Machine Learning, or you look at the breadth of results that are happening in RL right now, the vast majority of them are algorithmic and empirical. I would say that's dominated the field for the last 5 years since the Atari results. And I think part of this is because we are still building our understanding of deep neural networks, and deep neural networks for reinforcement learning have some of the same challenges as understanding deep neural networks in general, plus additional complications. So in some ways, there's quite a lot of more algorithmic or empirical reinforcement learning going on right now that nevertheless is very exciting in terms of its successes. On the other hand, reinforcement learning is deeply related to controls, like from the electrical engineering and other communities. It's very related to operations research. And so those communities have enormous history, at least since the 1950s. And I think one of the exciting things that's happening now is that we're bridging between these communities. So in fact, I'm going to be at UW in about 2 weeks again, because there's a workshop on the intersection of sort of controls and reinforcement learning. And there was one at MIT a couple months ago. So I think there's more and more excitement around the different communities as bridging between these communities to try to get at sort of some of the mathematical foundations and allow us to make progress. Okay, so now could we take the slides up? I'll go ahead and start writing on the board. I think that'll take them a second. We're now going to just start defining what a Markov decision process is and talk about some of the basic algorithms for computing policies. Can you see this in the back? Is that good? Okay. What's that? Those ones are better. This. Oh, I see. Okay. So the basic setting we're going to be in is we're going to assume an interaction between the world and an agent, where we're taking actions. We're generally going to denote those as AT, and we're going to receive some sort of observation and reward. And this, once the agent receives a new observation and reward, then they're going to continue. The goal in this case is going to be to maximize the expected discounted sum of rewards. Sum of rewards. And doing so in general is going to be assumed to trade off often between immediate rewards and long-term outcomes. So that's now that's going to be the issue that we're going to have to deal with delayed consequences. So for example, instead of coming to hear me lecture this morning, you could have gotten a really good coffee. That might have been better in the immediate term, maybe for your future RL. This is going to have been better to attend the lecture. So there are many cases we're going to have to trade off between immediate, perhaps more tempting outcomes and longer term rewards. Okay. So in this case, we could think of these as being all sorts of things. So this could be something like web advertising. And then the reward is whether or not people click. Now, in a bandit setting, we'd stop. We wouldn't continue this process. In the reinforcement learning case, then the idea is that depending on whether someone clicked or not, then you might take a different action next. So we can continue this process in that scenario. Now, the reward could be a number of different things here. It could be click-through rate. It could be how long they watch YouTube. It could be different types of things in that particular scenario. In that case, again, you would imagine that you might have to balance between immediate outcomes and longer-term outcomes. So the longer-term outcomes there could be that you're changing what people want to watch, or you're changing what people want to buy over time. And of course, this is something that marketing thinks about all the time, and this is one precise mathematical way to think about that. So another example is that this could be a robot unloading the dishwasher. The actions could be where does the robot move its arms to try to pick things up. This could really be very micro-level actions. And your reward might be delayed. You might only get a +1 when you completely empty the dishwasher. And so in that case, you're going to have quite a long delayed rewards before you actually get to see whether or not the actions you took are effective. So another thing could be something like blood pressure control, where you get to see whether or not you're in a target range, or something like whether or not people are healthy over the long term. I think one thing that's really challenging here is designing the reward function. Often we talk in reinforcement learning as if we don't know. I'm going to call the reward function R. Function R, which is just going to go to a real. This is typically going to be like a stochastic function. We often assume that we're learning this. Like in the case of Atari, the agent is learning whether the score goes up. But in many real cases, it's what humans design, and it has huge implications. So, for example, I think about intelligent tutoring systems often. I'll show you an example of this scenario, which makes the challenge sort of more apparent. So let's imagine a student doesn't know. There's going to be a student. We're going to be trying to learn to teach them, and they don't know addition, and they don't know subtraction. Sure. Okay. They don't know addition, and they don't know subtraction. There's only two things we're trying to teach the student, and there's a teaching agent that can either provide information, either provide like an addition question to work on or a subtraction question to work on. And what the reward function is here is they get +1 if the student gets the problem right. And also they get -1 if they get it wrong. Okay. So that's our reward function. The student starts off, they don't know addition or subtraction. Addition is an easier thing for them to learn. And this is harder. And what the agent gets to choose in this case is whether to give an addition question or a subtraction question. So if I set this as the reward function, what do you think my agent is going to learn to do if I tell it that its goal is to maximize the expected discounted sum of rewards? Yeah? Give addition problems, right? And forever. So this is a very simple example of reward hacking, right? Like we really don't want to only just, in fact, it would give them the first addition problem they got right, and then just give them that addition problem forever, because that would give infinite reward. That's sort of a silly example, but that's, the implications of that are much more profound. If we think about sort of using these on the internet to try to maximize things like click-through rate or how much time we're watching YouTube or other aspects, the choice of the reward function can be very subtle and very important. And I like to say that, maybe 10 or 15 years ago, some students I talked to had identity crises because they said, oh, all I'm doing is maximizing click-through rates and it doesn't matter, and so am I having an impact on the world? And now I think everybody says, oh my God, I'm maximizing click-through rates, I'm gonna destroy the world. So I think that these issues of how we pick the reward function and the fact that the algorithms are gonna do exactly whatever we tell it to do, whether that's to make all of us zombies into watching, videos forever or not, are really important, and it's really hard for us to get these right. And so I think there's also some really interesting questions right now around fairness and robustness and sensitivity so that we can identify when our reward function is wrong. Okay, so in the Markov decision process case, we're gonna assume we have this action, state, and reward, and we're gonna assume that the system is Markov. And so who here is familiar with Markov processes? Okay, most people are. Great. So what we're going to assume in particular is that our dynamics model, which is how our actions affect the next state of the world, so the probability of S prime given, I'll put this as T, given the previous state, the previous action, the state before that, the whole history of previous actions and states we've ever taken, is exactly equal to simply conditioning on the previous state and action. That previous state and action are sort of a sufficient statistic for us to predict the next properties. And that is a very, very common assumption in reinforcement learning. It is typically not true in most real cases unless you include the entire history of the states, entire history as your state space. But it's very popular, and it can be a good approximation, and it's going to have some important implications for how we're going to solve these.
Sorry,
Yeah.
between S sub t star and S sub t?
This is a typo.
Thanks.
Yeah. Okay. So in the bandit case, this would be like the identity function. So in a bandit case, this would just be probability of S. And you could think of this as where your actions don't affect the next state distribution, and so you're just always sampling from some fixed distribution. I'm not going to talk about it much. In the partially observable MDP case, we're going to need to condition on the whole history. For everything else, pretty much I'll talk about through the next 5 hours, we're going to assume this assumption. Okay. So in this case, we're now going to talk about, okay, so this is the dynamics model. We've got the reward model. I'm going to talk about 3 important things that we often consider in the case of reinforcement learning. So we have, when we talk about MDPs, we're going to define them as follows. We're going to say there's going to be a state space, an action space, a reward space, a dynamics model, and often a discount factor gamma. This is going to be a set of states. These could be vectors. They could be continuous state vectors. For today, we're going to assume that this is just a lookup table. So for right now, we're going to assume a lookup table. We just have a discrete set of states, or you could think of it as being a one-hop vector encoding. Okay. This is an action space. We're also going to assume for right now this is discrete. We have a finite set of actions. This is our reward vector. This is what I said earlier over here. Generally, it's going to be reward as a function of S and A. Depending on who you learn RL from, they'll define reward as the immediate state in action, or the immediate state, action, and next state. Pretty much all proofs and guarantees go through for all of these cases with very minor modifications. Most of the time, I'll use this definition. It's like I'm in a state, I take an action, and I get some real valued reward. This is our dynamics model, which is this probability of S prime given SA. And this is a discount factor between 0 and 1, which tells us how much we value immediate rewards versus future rewards. So this is a definition of a Markov decision process. And then once we have that, the major camps for how people try to do reinforcement learning with these, or try to compute an optimal policy. Our policy here, pi, is going to be a mapping from states to actions. So it's a decision policy, which allows us to decide what to do in a particular state. The major ways that people try to compute something of this that is good fall into 2 different camps. So one is model-based, which is coming up again in popularity. This has been particularly influential in the theoretical world. And this means that we're going to directly estimate and use R and T. So we're going to directly try to estimate a reward function in a dynamics model, and then we're going to use it in some way to try to compute a decision policy. Value-based methods are going to try to compute a value function. A value function is going to represent what is the expected discounted rewards of following a particular policy. So V pi is going to be equal to the expectation of the states that you're likely to visit if you follow pi. Let's assume for simplicity right now that we always start in a single start state. So I'll put here an S0. This is the initial state. But it could be a distribution of initial states. But for simplicity, we can think of there as being 1. So what would be the expected value, the expected sum of rewards we get from t equals 0 to infinity, weighed by the discount factor, indicating that we care about later rewards less than immediate rewards, times RT given the initial state was equal to S0. So this is the value function. This says how much reward do we expect to get, where the expectation, the reason this is an expectation is because our dynamics model is going to be stochastic. So we're going to think of getting to reach a sequence of states, and on average, what is the discounted sum of rewards of those sequence of states? So in a value-based case, we're going to think of value functions which have this definition and trying to maybe find a max over those value functions. And then the final approach is policy-based, where what we're going to try to do is we're going to find a policy arg max pi, maybe in some policy class, v pi. And these approaches typically rely strongly on the Markov property. So both of these leverage and assume, generally, Markovianness. This approach doesn't as much. We're not going to talk as much about direct policy-based approaches, but in terms of things that are empirically working right now, there's a lot of work on this side, and there's a lot of work on this side as well, on the direct policy search. Yeah?
So what's the difference between value-based and policy-based?
So it's in how we it's a great question. The question was, what's the difference between the value-based and policy-based? It's in how we compute this. So, and I'll explain that more in just a second. Okay. So, the question is whether or not we're going to end up assuming something about the particular structure of the world when we're trying to compute the value function or not. Yeah.
What's gamma plus?
Gamma t. So this is the discount factor raised to t. Okay. Yeah.
What's the expectation over here?
The states you would reach when you follow that policy. Yeah. So you can think of this as, for those of you familiar with Markov chains, if you follow a policy, then following a policy induces a Markov chain. And so you can think of the distribution of states you would reach in that Markov chain, and you would look at weighing the rewards you get under that. Yeah.
Just for clarity, you're assuming that the policy is a deterministic function, right?
Good question. Policy does not have to be deterministic. We'll talk about whether or not the optimal policy is deterministic. But you're right, here I wrote it as deterministic. You can also have this to be a probability distribution over actions. It can be deterministic or stochastic. Okay. Let me just put a couple more definitions up before we start to talk about how to solve these, how to actually compute this value function. So the horizon, H, is how many time steps we're going to make decisions for. Okay, so this is the number of time steps for decisions or actions you can think of all of those as being interchangeable at every time step, at every interaction. Every time step we'll take a decision or we'll take an action, and then we'll receive a new state and reward, and then we keep going. This can be infinite. This is essentially how many times does our agent get to make decisions before they're reset. So in an episode. So as an example of this, maybe you're treating patients and you have a 6-week course of treatments, and you're deciding on the sequence of treatments during those 6 weeks. And when that's done, a new patient comes in and they get a 6-week treatment. So in that case, we would have 6 weeks of decisions before we're reset back to the starting distribution. So in an episode, before we reset to S0. H can be infinite, which means that we just have one really, really long trajectory of experience. Yeah?
So is H the amount of time that elapses between like different policies being chosen? Is that...
Good question. The question is whether or not that's a gap between different policies. No, we can update within that, and that's critical if this is going to go forever. We can change how we're acting after every single state. You might not want to for computational reasons or for some other reasons, but in principle, your agent can think after every time it takes an action, gets a state, and receives a reward, it can change how it's acting in the world. Yeah?
Is the random variable?
H? Good question. We're generally going to assume that H in indefinite horizon processes, it will be. For most of what we're going to talk about, today we're going to assume it's infinite, or that it's a fixed length. We can handle also when it's a random variable. Like h can be a random variable, but for today, let's just think of it as being infinite. We're going to sort of act forever, and we're going to think about what would be the best way to act if we're going to act forever. Now, today, just for this first lecture, remember, we're not yet talking about having to learn these things. So we're assuming that someone has given you a reward function, and they've given you a transition model. Okay, so the definition of a return, in this case, GT, is going to be equal to a sum of rewards in an episode. So this would be kind of one rollout of your policy. You start in state S0, you take an action, and you go all the way out. So this would have to be under some policy pi, which was being used to make your decisions. Okay? So you decide how you're going to show ads to customers, or you decide which movies you're going to show, the movie recommendations you're going to show them on YouTube, and you see how long they watch until they log off. Or you look at the sequence of treatments you give to a patient and how well they're feeling each day, and you sum up sort of how well they felt across all 6 weeks. T equals 1. So we can either define this for a particular time step. I'll do it. Yeah, so you can either do, this can be, so this can, let me do it first for the starting case. So let's say we started in time step S0. This would be just the sum of rewards you get till the end of the episode. Okay, so we start off. Let me just write out what that would look like. So we start off in S0. I take an action, A0. I get a reward, R0. This action is selected according to my policy pi. Okay, so state, take an action, get a reward. Then I transition to a new state. This state implicitly was sampled from my transition model. Okay, so that's a tuple. So we start in state 0, we take an action from our policy, we got a new reward, that was sampled from our reward model, and then we get to a new state, sampled but from our transition model. Okay. And then we would take another action, another reward, ... Okay. And then the return would just be summing up all of those rewards. So G in this case, starting in S0, would be R0 plus gamma R1 plus ... Okay. So the return is just, the value function is going to be an average of returns. Where a return is like a single episode, a particular instantiation of the states you might reach following a particular policy. Because the world is stochastic, or could be stochastic, then if you run even from the same starting state for the same policy, you might get different trajectories. And then you would get, therefore, different returns. And so our value function here, I'll index this by pi. Because we're going to assume right now that the value function, that we're just thinking about trying to understand what the expected discounted sum of rewards would be for a particular policy. And so in this case, V pi of S0 is going to be equal to the expected G pi starting in state 0. So an average. So why do we, a nice question might be, why do we have this discount factor? It seems kind of weird. That means that we're sort of explicitly, remember gamma is between 0 and 1. Generally it has to be less than 1. And so we're going to assume that later rewards just aren't as valuable as earlier rewards. A lot of this is for mathematical convenience, as we'll see shortly. But there are some reasons to believe this is true if we think about, at least in many application areas. So for businesses, often they just don't care as much about very late rewards very far in the future, in part because there may be lots of other stochasticity that's going on. Okay. If you know that H is always bounded, let's say you're always optimizing for teaching people over the course of 5 hours, then maybe you can make h equal to 5, and then you can set gamma equal to 1. So typically, we're going to set gamma being less than 1 when we want to make sure that we can't have unbounded rewards. We can't have infinite rewards. Okay, so now the next question is, and this gets to the question from before, which is, is there any difference between here and here? Which is, how do we compute this value function? So one thing you could imagine doing in this case is you could just estimate this from simulation. So we're going to be in the setting right now where someone gives us, so we know S, A, T, R, gamma. Someone's given us all of this right now in this lecture. So for any state I'm in, I can sample a next state. I know exactly what my dynamics model is. I know exactly what my reward model is. And again, we're assuming that S is in a lookup table. It's just a discrete set of states. Okay, so how would we maybe compute the value of a particular policy? So let's say we want to compute V pi. Well, one thing you could do is you could just do simulation. So you know what the policy is. You have a mapping from states to actions. You know what the dynamics model is. You know what the reward model is. So one thing you could do, so how to compute? Simulate. I could just do Monte Carlo simulation. I could start in state 0. I could use my policy and my transition model and my reward model, and I simulate a return G. Does that make sense to everybody how we do that? So we just simulate out a trajectory. We could do this 100 times. We could do this as many times as like Hufting or something like that would tell us to get concentration inequalities on the expected value, and we could get a good accurate estimate of it. Now, the reason I bring this up is because if you're using simulation and you're using something like Hufting inequality to try to figure out how many samples you need until it'll converge, then you don't necessarily have to rely on the Markov property. This does not, don't need Markov. Okay. You're essentially not using any structure of the problem. You're just simulating out trajectories, summing up rewards, and then averaging over them. Yeah?
Isn't the simulation using the Markov property?
So the simulation could be, but from the perspective of this part of the algorithm, you could treat that as a black box, right? So there's some black box, and you're calling and you're saying, I've got a policy, give me a G. So G1, G2, dot, dot, dot. So you could have a black box here that outputs Gs. Okay. So this could be like, you know, the result for patients. You say, you know, what was their survival rate, or what was their survival for 100 patients? And I don't care what their dynamics model is. I just have a particular treatment policy, and then I observe the outcomes. So your simulator could rely on the Markov property, but you don't have to. Okay. But the insight is that if you know it's Markov, then there might be additional structure we could leverage. So if we know it's Markov, we have additional structure. Yields additional structure. And in particular, it's going to satisfy the Bellman equation, which a lot of the results that are on the model-based or value-based side are going to leverage the Markov structure and then therefore rely on the Bellman equation. So in particular, what the Markov structure is going to give us is that the value of a state is simply equal to the reward, let me put it for a particular policy, pi. Sure. Is equal to a state. This here, I'm implicitly assuming the policy is deterministic. But again, we could relax this and it could be stochastic. But for simplicity, let's just assume a deterministic policy. We'll see soon that that's sufficient. So the value of a state under a policy is equal to the immediate reward you get plus the discounted sum of future rewards. And what's the discounted sum of future rewards? It's the probability of us transitioning to any other state. So I'm starting in this state, I'm taking this policy, same policy is there. I'm going to have some probability according to my dynamics model of transitioning to any other state. And then the value of that next state. So this is just the discounted sum of future rewards. So it has this really nice decomposition because we don't have to worry about all the previous history here. We can say immediate reward plus all the next states we could get to and whatever their value is. So right now this is for h equaling infinity. And gamma has to be less than 1. So if this is an additional property we get if the world is Markov. So we're going to be able to use this to think about how to actually compute what the optimal value function is and what the optimal policy is. The optimal value function is going to be the value function that maximizes the expected discounted sum of rewards. I'm going to erase this here. And the optimal policy is going to be the policy that realizes that optimal value function. Let me take it down, and then we'll write down an algorithm for solving for that. Okay. So V star is going to be the max over all policies V pi. And pi star is going to equal to the argmax. Pi V. So this is simply the policy that maximizes the expected discounted sum of rewards and the value function, the actual expected discounted sum of rewards for that policy. This is the best way to act if you care about maximizing expected discounted sum of rewards. And what the Bellman equation tells us, which looks very similar to the equation that I just wrote up there, is that V star, so our optimal value function, is equal to argmax A, your immediate reward, plus gamma some probability of S prime given SA, V star of S prime. So the Bellman equation tells us that the best possible value of a state is equal to taking an argmax over all immediate actions you could take that maximize my immediate reward plus my expected discounted sum of rewards if I were to continue to act optimally from that resulting state. So I need to, and this is going to induce sort of a dynamic programming-like algorithm. Because what this is saying is that in order for me to act optimally, what I need to know is that for all the states that I might reach after I take an action, if I could act optimally from there, and then I act optimally now to get to those states, then that's going to give me my optimal value function. So this is the Bellman equation. So this immediately introduces a natural algorithm for trying to compute this, which is using dynamic programming. So this is the value iteration algorithm. And what value iteration does is it says we're going to initialize V0 of S equal to, well, anything, 0, for all S. So we're going to initialize the value function. Right now, again, the state space is discrete. So this is just a lookup table. We're initializing our vector to be 0 everywhere. And then, and what we can think of this here is, this is the value function. This is the expected discounted sum of rewards, the optimal expected discounted sum of rewards, if we make no decisions. We get zero rewards everywhere. Okay, and what value iteration is going to do is compute at each step what would be the optimal expected discounted sum of rewards from acting from that step forwards. So what value iteration then says is for k equals 1 until Or I'll write it as while. Oop. I'm going to do v, that's how, vk, and then I'm going to say k equal to 1. So for vk of s, this is going to be equal to exactly that Bellman equation. So I'm going to do what's called a Bellman backup. Word of SA plus gamma looks almost exactly the same as this equation, except for instead of using v star, I'm going to use the v from the previous round. Okay, so I do what's called a Bellman backup, which says I used to know what the optimal value function was if I had k more time steps to make decisions, and now I'm going to think about what the optimal value is if I get k plus 1 more time steps to make decisions. Okay, so I started off, I knew what the value was if I'd make no decisions. Now I'm going to compute what should be the value if I make one decision. Yeah.
Argmax and not the max?
Thanks. If you want to extract the policy at the end, then we use the argmax. Okay.
So that you can iterate over all of S.
Yes. So we're in the tabular setting right now, and we're hoping it's not too large. And one of the questions for the recitation is thinking about what is the computational complexity. So yes, if S is very large, if S is, 10 to the 6 or something like that, this is going to be very expensive. There are other ways to do this where we don't necessarily have to iterate over this. I'm going to show you, this is going to be the simplest setting. Okay, so in general, as was just brought up, this is going to be an order S squared A operation. Because we're going to be doing this for all actions and then taking the max, we have to do this for all states, and we have a sum over all next states. So it can definitely be expensive. So we do this, and when do we break? So we want to break when we've converged. I'm going to have to convince you in a second that we do converge. If you do, we will converge, and we often want to break if the max difference over the infinity norm, so we look at just the maximum difference for any of the states, is less than or equal to epsilon. You'll typically have an epsilon input, which says what's the level of accuracy you want for your value function. It could be 0.001, depends on your choice. And essentially, you can break when this has converged to a very small point.
Two subsequent steps, k and k minus 1 over there, and then blue, and then 1.
K minus 1, thank you. And then the k will have to be equal to k plus 1. So each time we're starting with it, we start off, we do a Bellman backup. We do that for all states. So this is for all states. Then we check to see whether or not for any of the different states, if their value has changed by more than epsilon. If none of them have, we break. All right, so the question is whether or not this converges. It does converge because the Bellman backup is a contraction operator if gamma is less than 1. So who here's seen that proof before? Okay, a couple people, but not everybody, so let's go through that. Okay, so let me erase part of that. Just for 1 second. Okay, so we're going to prove now that the Bellman backup is a contraction operator in the case where the state and action space are discrete. Should be able to get it in here. Okay, so what we're going to assume is I'm going to be assuming that put this definition here. I think you've seen this definition before. We're going to assume v minus v prime. If I use this notation and I don't put a subscript, I'm going to be assuming an L infinity norm. And just to be totally concrete, that means that in this case, for our discrete set of states, it's going to be looking at v of s minus v prime of s. So just the absolute difference between those. Okay, so what we want to be able to prove is we want to be able to prove that this thing is going to converge to a single fixed point, which is going to tell us that there's a single optimal value function and that value iteration is an algorithm that allows us to achieve that. And so what we want to prove in this case, I'm going to use b here, b vk minus 1. So for sort of shorthand, we can think of applying an operator denoted by b to vk minus 1 here. And what it means for us to do that is to do this equation. That is the Bellman operator. So what we want to do here is we want to compare what happens when we do the Bellman backup between two different value functions. And what we want to show is that the distance between these two gets smaller after we do a Bellman backup, indicating that the operator is a contraction. So we're shrinking the distance between these two, in this case, vectors. So what is this equal to? We're just going to write out what the Bellman backup is. So we've got a max over A of R of SA plus gamma sum over S prime, probability of S prime given SA of VK of S prime. Minus, and I'm going to use a different A here, max over A prime, R of S A prime, plus gamma sum over probability of S prime given A prime, S, V, J of S prime. Okay. So I'm using a different A here because these are two different value functions. And so when we do a Bellman backup on them, we might end up picking different actions in each case. Okay. But we know that this difference can only get wider if we restrict this action to be the same as this action, right? Because either A prime is equal to A, in which case it doesn't matter if we do the substitution, or A prime is something where this whole quantity gets smaller if we pick a different A. So this is one of the first important steps. So this is less than or equal to just doing a single max over A of R S A plus gamma sum over probability of S prime given S A, VK of S prime minus R of S A minus gamma sum over probability of S prime given S A, VJ. Okay. But that's nice because then we can then cancel these two things, cancel the reward function. So this is equal to max A plus gamma, max A, gamma, sum over probability of S prime given SA, VK of S prime minus VJ. Okay, I just canceled that part. Okay, and so then we can just simply say, well, this is going to be less than or equal to max A gamma sum over probability of S prime given SA, because this is always a positive quantity, so we can do this. And then we're going to take an absolute value here over VK S prime minus VJ. Okay. So I just move the absolute values in. Okay. And then in this case, we can upper bound this by whatever, by our L infinity norm. This is always less than or equal to the max difference over any state, but that's independent of S prime, so we can move that out. So this is less than or equal to max over, we don't have an A in it, well, okay, still have an A so far. A gamma VK minus VJ, sum over probability of S prime given SA. Okay, this is just our probability distribution, so this sums to 1. So this is equal to gamma. Okay. So what that says is that as long as our gamma is less than 1, then the difference after we do a Bellman backup between two value functions has shrunk. So now things are closer. So you can imagine gamma might be something like 0.9. So whatever our max distance difference was between any states for our value function is now smaller by a factor of 0.9 at least. And that's true even if all of these things are equalities because gamma is less than 1. Yeah?
Why the action has to be the same in the second?
Oh, why we get an inequality there? So what I've done here is, so this here, these two actions, good question. The question is about changing these actions. So here, this is the action that we would get by doing a Bellman operator on VK. And this is the action we would pick if we were maximizing the expected discounted sum of rewards using a Bellman operator with VJ. So in general, A prime and A will be different, or certainly could be. What I'm saying is that that difference between those two value functions can only get wider if I force this to pick the same action as here.
This is not necessarily true only if the second max is smaller than the first.
Oh, good question. Okay, so what I'm assuming here implicitly is that the rewards are all, everything's positive. And that the rewards are all between 0 and 1. That's a common assumption. We can scale everything. But as long as that's the case, so as long as our value functions are bounded between 0 and some positive quantity, then if we max here versus forcing this to be action, forcing this to be the same action as this quantity is only going to get smaller. So we're subtracting something smaller, which is making this bigger. So that's sort of this part and this part of the two main ideas for that part. Okay, so what this shows us here is this is a contraction operator. And because this is a contraction operator, because Bellman operator is a contraction, that means there's a single fixed point. Because if there was more, so that this implies that the Bellman operator is a contraction, which implies V star is unique. Okay. Does anybody have any, want to comment on why V star has to be unique? Or did you want to?
Doubt on the previous one. So there's still an implicit assumption that the VK is larger than VJ or something like that, right? Because otherwise you could have something that's going to shrink the gap rather than expand the gap.
But now I'm maximizing the, sorry, I guess, do max over A here. That would, I think, address the issue. I'm picking the action that is going to maximize this gap between these. I think that'll address the issue. So this case, we were picking two different actions. And now what I'm going to say is instead of doing that, I'm going to pick one action such to maximize this difference. But that's still going to be, should we still want it to be here? So say your question again. Yeah. So we're going to want to pick this in a way that this whole quantity is maximized. Okay. And that's going to be equivalent to us dropping this part. Good questions. I'm also generally going to be assuming this, particularly for a lot of the exploration part. So the Bellman operator is a contraction, which means that there's only going to be a single fixed point, because if there was more than one fixed point, we could apply the Bellman operator and then shrink the distance between those two. So the fact that the Bellman operator is a contraction means that V star is unique, which means there's a single optimal value function. Can anybody answer me whether or not there is a single optimal policy? No. Yeah, in general, there could be. It depends on the problem. But pi star is not necessarily unique, not always unique. And that's because you can have ties. So V star is unique, but pi star is not necessarily unique. There could be two policies, two optimal policies that both have the same unique V star. Okay. So I think I'll probably halt there. This is sort of the most value iteration is a basic algorithm for computing the optimal value function of a policy or optimal value function of an MDP. And it's been extended to the deep learning case where we start to, instead of being able to do all of these things exactly, we can start to use regression to approximate the Bellman backup. So we'll talk more about that later. And then in the recitation, you'll have a chance to do this sort of computation and think about some of the proofs that are related to it. Thanks.